Okay, so we're going to look at the Pythagorean identities and their alternate forms. So what are the Pythagorean identities? They are equations relating the trig functions using the Pythagorean theorem. Okay, so that's what the Pythagorean identities are. So the first thing we'll do is we will look at a right triangle where the hypotenuses are. So if we create a right triangle with hypotenuse r and call this angle theta, then we know that the side adjacent to theta would be the hypotenuse times the cosine of that angle, and the side opposite theta would be the hypotenuse times the sine of that angle, theta. Okay, this is pretty simple to see. Now, if I shrink this triangle by a factor of r, then what I end up with is a right triangle where the hypotenuse is 1. The angles remain unchanged. The sides are what change, so r divided by r is 1. And if I divide the adjacent side to theta by r, I just simply get the cosine of theta, and the opposite side becomes the sine of theta. And now I have the lengths of the three sides, and notice these two sides depend on the sine of the angle and the cosine of the angle. So using the Pythagorean theorem, I can see that cosine of theta squared plus sine of theta squared equals 1 squared. And we already know, or may know, that we could rewrite the trig function squared in a different form to avoid writing the parentheses. So if I square the cosine of theta, I can write that as cosine squared of theta plus sine squared of theta equals 1. This is our first Pythagorean identity. One thing to note here is that the angles are the same. So if this was theta and this was phi, this would not be a true statement. But if the angles are the same, then I could take the cosine of the angle, square it, add it to the sine of the angle squared, and I would get 1 every single time. Now, let's look at the other two Pythagorean identities. There are 3 of them. The last 2 are based on the first one, and we get the last 2 by dividing the first one by either dividing both sides by cosine squared or by sine squared. So for example, if I divide both sides of this equation by cosine squared, this cosine squared becomes a 1. And if I divide the first equation by sine squared on both sides, the sine squared becomes a 1. Okay? Now, let's look at what happens here. So to get the second one, we divided by cosine squared of theta. And to get the last one, we divide by sine squared of theta. So we end up with, of course, and let's do the second one. Cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared, well, sine divided by cosine is tangent. Sine squared divided by cosine squared is tangent squared. 1 divided by cosine squared, well, 1 divided by cosine is secant, so 1 divided by cosine squared is secant squared. And finally, if we look at the last one, the last Pythagorean identity, I'll divide my first equation on both sides by sine squared. Cosine divided by sine is cotangent, so cosine squared divided by sine squared is cotangent squared. 1 divided by sine squared is cosecant, so 1 divided by sine squared is cosecant squared. Sorry, I don't recall if I said that wrong. 1 divided by sine is cosecant. 1 divided by sine squared is cosecant squared. And now we have our 3 Pythagorean identities. The last 2 are based on the first one, and the first one was based on the right triangle using the Pythagorean theorem that we looked at. Now, I I encourage you to derive these many times so you can start to do it more quickly in your head. In fact, that's usually what I do. This first one is essential. This one you should know like the back of your hand eventually. And then if you just imagine dividing by cosine squared or just imagine divided by sine squared, you can easily get these last two. But I also start to remember that the first one relates sine and cosine. Then I've got one that relates, let's look at the last one. The last one relates to cos that aren't sine and cosine, so cotangent to cosecant. And the middle one relates the only two that are left that aren't cos, and they aren't sine and cosine, so tangent and secant. And so these equations relate the trig functions in different ways. But these aren't the only ways that I've got listed here. These are the most common ways. Let's look at some alternate forms of these Pythagorean identities. And before we do that, I need to maybe show you a little bit about reciprocals. So first of all, let's look at 2 and 1/2. Of course, they are reciprocals. So what does that mean mathematically? Well, the obvious one is 1/2 equals 1 over 2, the reciprocal of 2. Similarly, 2 equals 1 over 1/2, or 1 divided by 1/2. So the relationship between reciprocals is one number equals 1 over the other number. So, for example, how does this apply to trig? Let's get rid of this. How does this apply to trig? Well, let's look at cosine. Cosine of theta and secant of theta are reciprocals. So, of course, we're already comfortable with the fact that secant equals 1 over cosine, but also cosine equals 1 over secant. Okay, so this is what we'll sort of use here to get an alternate form of this first Pythagorean identity. So let's see one alternate form. I can replace cosine with its reciprocal form. In other words, I can replace cosine with 1 over secant. And cosine squared becomes 1 over secant squared. And I could leave my sine squared alone. So that's an alternate form of this Pythagorean identity. Now, this equation, which related cosine and sine, we've changed it so that I can relate secant to sine. And I could do the reciprocal forms of both of these. I could have 1 over secant squared theta plus 1 over cosecant squared theta equals 1. I can do any or all reciprocal forms. So you can look at those, some other reciprocal forms. You could also take and solve for any part of this. For example, if I solve for cosine squared of theta, I would subtract sine squared theta from both sides, and I'd get this. This is actually very common because now I can replace any place I would see a cosine squared of theta, I could replace with 1 minus sine squared of theta if I wanted to change from cosines to sines. And you could, of course, solve that for different things as well. So solving for one term is another way to get alternate forms. Finally, if I look at rewriting the second one, now that on the right side I have a minus, over here everything was added. But here I have a minus. This is now a difference of squares, which will factor as 1 minus sine theta times 1 plus sine theta. So using factoring. And you can get some other forms that way. So there are many, many alternate forms of these equations. You can use the reciprocals, you can solve for a piece, and you may be able to use things like factoring to write it differently. Okay, so let's look at alternate forms for the second one here. And we'll use the same principles. For example, I could write this with reciprocal forms. So the reciprocal of tangent is cotangent. So tangent squared is the same thing as 1 over cotangent squared equals secant squared is the same thing as 1 over cosine squared, if I wanted to relate cotangent and cosine. And of course, I could solve this for whatever I wanted. I could get all sorts of different forms, and the same thing with the last one. So you could use reciprocals. You could solve for a piece, and you could potentially factor if you can get a difference in there somewhere. Those are the Pythagorean identities. I want to close with one last thing about these. That should be obvious, but if you look at this one, this second identity, these both have a cosine squared on bottom, because tangent sine over cosine, secant's 1 over cosine. And the last one, both of these have sine on the bottom because cotangent is cosine over sine, and cosecant is 1 over sine. So they have common denominators that might help you remember them in a different way.